All right, welcome everyone. Today we're going to move into our new topic, improper integrals. And in this lesson, we're going to see how we can sort of generalize our definition of the definite integral to, well, include what we're going to call improper integrals. And these are really a couple things. They might be integrals over infinite intervals. Try saying that fast. Integrals over infinite intervals, or they might be integrals of functions that have an infinite discontinuity. So we're going to be dealing with a lot of things moving to infinity in this lesson. And so by the end, we're going to be able to determine whether an improper integral is convergent or divergent. We'll see what those terms mean. And then we'll see that if an improper integral is convergent, we'll be able to actually evaluate the integral. All right, so first, a little review. We saw this back in Calc 1, and this is kind of the main theorem. This is the big show, the fundamental theorem of calculus part 2. This is really motivates most of what we do in this course, and that's calculating a definite integral. So let's just read through what this fundamental theorem of calculus part 2 says. It says, if a function f is continuous on the closed interval from a to b, then the definite integral of f of x over that interval from a to b is equal to, and we find an antiderivative capital F, and it can be any antiderivative. And then we plug the upper limit in, we plug the lower limit in, and we subtract. So this is what we're used to. This is how we normally calculate a definite integral. Now, hidden in here, there's actually two conditions for this theorem to work. So the first condition we see right here. We're talking about a closed interval. So there's really two conditions for this theorem as it's written, and that's our interval is, well, it's a closed interval, but it's also finite. It's bounded. So that's the first condition. We've only defined definite integrals when we have this nice closed, bounded, really finite interval here. We're going to relax that. We're going to see how we can kind of relax that condition and see what we get. The other condition is that our function f has to be continuous. The function that we're integrating, we want it to be continuous for this theorem to work. Now, in Calc 1, we saw that we could already relax that a little bit if we had jump discontinuities or holes in our graph. We could still integrate it, for a certain extent. But we're really going to look at what happens if we relax this condition. And that's the second one. F is continuous. So we're going to see what happens when we look at intervals that are not finite and functions that are discontinuous. And we're going to see how we can actually define a new type of integral based on relaxing some of those conditions. And that's the first one we're going to look at. We're going to look at what happens when we try to integrate over an infinite interval. And it's going to start with our first definition. And I like to call these right-hand improper integrals. So let's read through the definition, and then we'll talk about the interval that we're actually dealing with here. So if f is continuous for x greater than or equal to a, then we're going to define this new type of integral where This is an improper integral. It's the improper integral of f of x over the interval from a to infinity. And how do we actually define this? Well, infinity is not a number that we can just plug in. And so the only way we can deal with this is we have to sneak up on it. We have to approach it. So we're going to write this as the limit as b goes to infinity of the integral from a to b of f of x dx. So this is going to be our working definition here for these types of improper integrals. And we're going to really explore what this right-hand side really means. And what does it mean when we're doing the limit as b approaches infinity of this definite integral? All right, so in this definition, we're really looking at the interval when x is greater than or equal to a. So this is really talking about the infinite interval starting at a and extending infinitely far to the right. That's why I like to call it the right-hand improper integral here. So this, we're going to see, well, it already relaxes the one condition from our fundamental theorem of calculus in that we don't have a closed and bounded set here. We don't have a closed and bounded interval. It's not a finite interval. We're now extending this interval infinitely far to the right. And as we're going to see, in some cases, we can actually do this and get something meaningful. So we say that this improper integral is convergent if that limit exists. So sometimes it's going to exist. We can do this. We can actually calculate this limit. Other times that limit is not going to exist. So it depends on the function. And we say that the improper integral is divergent in that case. All right, so we're going to refer back to this definition. Now, how do we actually interpret this? What are we doing when we're calculating the limit of a definite integral? Well, we're going to think of it in terms of area. So we know for definite integrals, a lot of times we think of that as area under the curve. And so for our purposes, if we have a non-negative function, so it doesn't go below the x-axis, we can interpret the improper integral as really representing the area under the curve of y equals f of x for x greater than or equal to a. So when we write and when we calculate the integral from a to infinity of f of x dx, really we can think of this, if that limit exists, if that integral exists, we can think of that as the area under the curve. And that's for a function that doesn't go below the x-axis. So we do have this little bit of wording here. Non-negative means on or above the x-axis. So when we graph our function here, in this little example here, the function looks to be always above the x-axis. Looks like it starts getting close here, but we're going to interpret that as it's really close to the x-axis, but it's slightly above. It has a horizontal asymptote. So non-negative means we're on or above the x-axis. The graph never kind of dips below the x-axis. And so really when we calculate this improper integral, we're thinking of it as really calculating the area starting at x equals a. So our region is going to start at x equals a, and then it's going to extend infinitely far to the right. It's under the curve, and our region is going to extend infinitely far to the right. And as we're going to see, sometimes this region, even though it's unbounded, it keeps going further and further, sometimes this region is going to have a finite area. And that's when our improper integral is convergent. The other times is when our improper integral is divergent. Well, then the area is just getting, possibly it's getting really large. It's just approaching infinity. So convergent, we can really think of a convergent improper integral as really having a finite area. So this region under the curve has a finite area. And if it's divergent, well, then we can think of our non-negative function as having an infinite area under the curve. All right, so let's try some examples. We're going to first kind of work with our examples, and we're going to refer back to these types of pictures quite a bit as we develop our intuition for what's going on with these improper integrals. So let's try an example. Example 1. We're going to determine if this improper integral, the integral from 0 to infinity of e to the negative 2x, we're going to determine if that improper integral is convergent or divergent. And if we find that it's convergent, we're going to find its value. Now, first of all, how do we know it's an improper integral? Well, we look at the interval that we're integrating over, and it's from 0 to infinity. So that's one of our infinite intervals. All right, so what's the process here? Well, let's start by just writing a nice fresh integral. Integral from 0 to infinity of e to the negative 2x. Now, infinity is not something that we're just going to be able to plug in. We have to use that definition. So this is the key first step, is we're going to rewrite this as the limit. We're going to use that definition. And we're going to rewrite it as the limit as b goes to infinity of the integral from 0 to b of our function. So how we're actually defining this improper integral is infinity is not a number that we're just going to be able to plug into this. We have to approach infinity. We can only let the upper bound get larger and larger here. And so this is the key first step. We have to use that limit definition to rewrite this as something we can actually calculate directly. And so we've essentially taken that infinity off of our upper limit, and we've done the only thing that we can do with infinity is approach, do a limit. So we're doing the limit as the upper bound gets larger and larger, as the upper bound approaches infinity. So this is always going to be our first step. When we have an improper integral, rewrite it as a limit. All right, so once we do that, then it's going to be kind of going through our usual motions for a bit in terms of doing some integration. So we have this definite integral right here, and we're just going to calculate it, just like we normally would. So we're going to calculate this like usual. Forget about the limit in front for a minute. And we're just going to calculate this definite integral just like we normally would. All right, so let's find the antiderivative. So what's the antiderivative of e to the negative 2x? Well, that's one of our k form. So it's going to be e to the negative 2x. And then we take that constant that's in front of the x, flip it, put it in front. So that's just one of our kind of usual k-form integrals. If you don't remember that, you could do a u substitution where you let u equals negative 2x. All right, so that's our antiderivative. And then we need to evaluate this from x equals 0 to x equals b. So we found our antiderivative just like normal. We're going to evaluate it just like we normally would with a definite integral. All right, so the top number goes in first, so we plug that in. So we're going to end up with negative 1/2 e to the negative, and we're kind of keeping this upper limit as, right now it's just a general constant. So right now we're letting it equal b, and that's what we're going to plug in. So it'll be negative 1/2 e to the negative 2b. Still writing that limit sign in front. We still have to do that, but we're just kind of going through the integration right now. All right, so that's our upper limit. Now let's plug in our lower limit. So we're going to plug in 0, plug that into our antiderivative, and we end up with negative 1/2 e to the 0, and e to the 0 is 1. So just a negative 1/2 there. All right, and then we subtract. So top number goes in first, bottom number goes in second, and then we subtract just like we normally would with a definite integral. Let's simplify this now. So that's really step 2, is go through, find the antiderivative just like you normally would, evaluate that antiderivative just like you normally would, and then we're going to get into the new part here. But before we do that, let's just clean this up. So I have a double negative. So I'm going to write that as a positive, and I see that this other term has a negative in front, so I like to put the positive term first just so I don't lose track of any other negatives. So I'm going to put the positive 1/2 first, then I'm going to have minus 1/2, and for the purposes of actually calculating this limit, I like to convert any terms with negative exponents, I like to convert them to a fraction. Just rewrite it as a fraction. So instead of e to the negative 2b, that negative exponent means it's just the reciprocal. So 1 over e to the 2b. All right. So now we're in a position where we can actually calculate the limit. So we first rewrote our improper integral, then we went through and actually just did the integration. Now we have it in a format where we can actually calculate this limit. And let's go through. So we're going to go through term by term and just think about what the limit is for each of these expressions. So first of all, what is the limit of this 1/2 in front here, this first 1/2? As b goes to infinity? Well, this is just a constant, so the limit of a constant is whatever the constant is. So it's just going to be 1/2. Then we have minus 1/2. So again, that's just a constant multiple, so it's just going to stay whatever that constant is. And then let's look at this fraction here. And b is approaching infinity. So that means this exponential term is approaching infinity. And so what we have here is we have this fraction where the denominator is getting really large. It's going to infinity. And so that means the entire fraction goes to 0. So what do we end up with here? We end up with 1/2 minus 1/2 times 0. Anything times 0 is just 0. And so we end up with 1/2 as the value. And that's it. So the fact that we get a number here tells us our improper integral is convergent, and the value of our improper integral is 1/2. All right, and that was step 3. So there's really kind of 3 steps here. It's rewrite it as a limit, calculate the definite integral, and then evaluate the limit. And we just want to keep track. Really, why this 1 over this exponential went to 0 is because b was approaching infinity. That meant the exponential e raised to the power 2b approached infinity. was getting larger and larger positive. And so when we have a fraction where the numerator stays constant and the denominator gets larger and larger, the overall limit of that fraction goes to 0. So we might consider this like a 1 over infinity form. We can't plug in infinity, so that's not actually what our limit is equal to, but a 1 over infinity form tells us that the limit goes to 0. So that's kind of what we're thinking in our head. When we have this fraction where the denominator is getting really large, well then the whole fraction is getting closer and closer to 0. All right, so that's the general process. Let's just see what we did here in terms of calculating an area. So here's the graph of our function. So this is the graph of e to the negative 2x. You can see it has that exponential look to it. Now it's a negative 2x, so it's exponentially decaying here as we move further and further to the right. And we started at a equals 0. So you can see we started right here at a equals 0. And what we've done by calculating this improper integral is effectively we've found the area of this region under the curve that extends infinitely far to the right. So the area under the curve here is, what is it? It's, what did we find? It was 1/2. So the area under the curve f of x on the interval, let's say on the interval, is equal to 1/2. So even though this region, you know, if we went really far out along the x-axis to the right here, if we went really far out, we'd still see part of our region. It would be really thin, but we'd still see part of our region. So this region that we're finding the area of extends infinitely far to the right, but it actually has a finite area. So that's actually pretty surprising that we're able to kind of deal with these unbounded regions that extend infinitely far in one direction, but still get something that has a finite area. All right, let's try another example. So let's look at the improper integral of from 2 to infinity of the function 1 over square root 3x plus 5. We're going to do the same thing. We're going to determine if this improper integral is convergent or divergent, and if it's convergent, we're going to find its value. Now first, why is this an improper integral? Well, it's because we have an infinite interval here. So we're going from 2 to infinity. All right, let's go through the process again. Try this one out. So we're doing the improper integral from 2 to infinity of 1 over the square root of 3x plus 5 dx. Very first thing we do, rewrite that improper integral as a limit. So we're going to write this as the limit as b goes to infinity, and we're replacing that upper limit, instead of infinity there, we're replacing it with a number now. It's actually a number, b. Very first step. Rewrite your improper integral as a limit. Now, what we have here is, this is just a regular, good old-fashioned definite integral. We can use all of our techniques. So let's go through, this is the second part of it now, go through and actually calculate this definite integral. And to help us with this, let's first rewrite our function. And we're going to rewrite it as with a negative exponent. and also as a fractional exponent so we can get rid of the root sign. So this is just going to help us find the antiderivative. So we're going to write this as 3x plus 5 raised to the negative 1/2. Kind of our usual, process for doing antiderivatives when we have, possibly a fraction or possibly a root function like this. So we can really rewrite it as a power function. Now, why that's helpful is because this is just a power function now that we can kind of do a mental substitution for. We can figure out what this one is. So what's the antiderivative? Well, we're going to keep what's inside the parentheses the same, so 3x plus 5. We're going to add 1 to the exponent here, so that's going to take us up to positive 1/2. We're going to take that new exponent, flip it, put it in front, so that's going to give us a 2. And this is one of our K-form type integrals. So it's almost power rule, but we have to do a little bit of a substitution here. And we have this constant in front of x, so we're going to take that constant, flip it, put it in front as well. So we're going to have a 1/3 in front. So if you want to go through the details here, you could do a u substitution where you let u equal the 3x plus 5, but this is really just one of our K-form type integrals where it's a pretty easy substitution. So we can just kind of figure that out. All right, so there's our antiderivative. Now we're going to evaluate it. So we're going to evaluate this from x equals 2 to x equals b. And so let's plug in. Top number goes in first. So what do we get when we plug in b? We're going to plug b into this antiderivative. So we're going to end up with 2/3. Let's combine those into one fraction. And then we'll have 3b plus 5 raised to the 1/2 power. Then let's plug 2 in. So we're going to plug 2 into our antiderivative. So we're going to have 2/3 times what? 6 plus 5. So 11 raised to the 1/2. And then we subtract. So that's that's kind of the middle part of our work here. First step, rewrite this as a limit. Step 2, calculate the definite integral. So we have a whole grab bag full of techniques now, so you might have to use some of those in here. Once you get it to a point where you've actually evaluated the definite integral, you might simplify. This is already pretty simplified, so now we're going to actually go through and calculate the limit of this. And that's the third step, calculate the limit. And if we look at this, we're going to kind of think about it. We're going to think about it term by term here. And let's remember, b is approaching infinity. So we have this expression here, this 3b plus 5 raised to the 1/2. Well, what's happening to b? It's getting larger and larger positive. So what happens to 3b plus 5? Well, that gets larger and larger positive. Well, what happens when we take a really large positive number and do the square root? Well, we still have something that's a really large positive number. And it's still, as we let that number get bigger and bigger, the square root of it is also going to get bigger and bigger. So this limit, this whole first term, is just getting larger and larger. Doesn't matter what the second term is doing because this is all just constants here. So this isn't changing at all, but this first term is getting larger and larger. So as b gets larger, this whole first term is getting larger and larger positive. So the overall limit here is infinite. So you might be kind of thinking here, b is approaching infinity. So b is getting larger and larger positive, which means 3b plus 5 is getting larger and larger positive, which means 3b plus 5 raised to this positive exponent, 1/2, is getting larger and larger. So it's approaching infinity. All right, so we're probably, at this point, we're going to have to dust off some of these limits at infinity. So, we've kind of given some intuition about why these expressions are approaching infinity or approaching a constant as b approaches infinity. We're going to have to go back and actually talk about some of these limits in a little bit more detail, just because it's probably been since the beginning of Calc 1 since we've really worked with limits at infinity. So this is going to be something we're going to just kind of go through some usual limits at infinity that we're going to see. But that'll be for next time. So what we've just shown in this expression is that this entire limit is getting larger and larger. And so what that means is the limit technically does not exist. And so our improper integral is divergent. All right. So let's see what we just calculated. So here's our function here's the graph of our function that we just integrated, or tried to at least. We started at x equals 2, and we tried calculating the area for this region that started at x equals 2 and extends infinitely far to the right. But we saw that that limit was infinite. So here we have a region extends infinitely far to the right, but it also has an area that's infinite. And we know it's infinite because this function is above the x-axis, and we calculated the improper integral and saw that the value of that improper integral was infinity. So an interpretation of that is that this area, has an infinite area. All right, so let's just kind of review the procedure here. When we have an improper integral, first step, we rewrite that improper integral as a limit. Step 2, we're going to integrate our definite integral. So we've taken infinity off of our limit, off of one of our upper limits there, and we're going to calculate that definite integral just like usual. So all of our integration techniques. Once we go through the evaluation there, we're going to calculate the limit as b approaches infinity. So we're going to actually calculate the limit. And so next time, we'll kind of just have a nice little review for these limits at infinity, now that we see that it's going to be something we're going to be working with quite a bit in the examples here. So being able to calculate those limits at infinity is going to be important. But that'll be for next time. All right, so we'll continue on with improper integrals, the exciting world of improper integrals, limits at infinity. And these are so good. They really get everything here. We get some Calc 1, we get some Calc 2 here, and we're going to be really using improper integrals later on in the course as well. So this is one of those sections where we're gonna come back to it. So we'll press on next time. So have a good rest of your day. We'll see you tomorrow. Bye-bye.